Okay, Dan and everybody, it's we've just hit 6 minutes, so we do need to get going. So good evening. My name's Brian Lawson. I'm the Technical Director for Projex Solutions. We're a project management and engineering services company. We've got a base in West Yorkshire and in sunny Teesside up in the northeast. We're hosting these lectures in support of the West Yorkshire area IMechE committee. So anybody that's interested in volunteering and members of the IMechE, please feel free to reach out to me and we'll get you hooked up. This is the last STEAM lecture in the series of 8, Decarbonizing STEAM. So a little bit of a window into the future. And this series of lectures kicked off being synchronized with the University of Huddersfield's start of the year, or start of the first term. So it's thanks to Josh and Carl from the engineering department at the University of Huddersfield. The lectures will be being aired over Teams, as you know. They're presented by Dan Wells, who's the National Consultant Specialist for Spirax Sarco Ltd. In a moment, I'll hand over to Dan. Just some very basic logistics. The presentation will last about 50 minutes, with the opportunity for questions and answers at the end. But please post any questions via the Teams chat function. You should see there's a button at the top saying Q&A, and I'll monitor these as we go, and if it's appropriate, we might even interject and answer it as we go. As I mentioned, this is the last in a series, so a big thank you for Dan, who's interrupted his evening for the 8th time now to bring these lectures to us. So without further ado, it's over to you, buddy.
Great, thanks for that introduction, Brian. And as previously, I'd really like to extend the thanks of Spirax Sarco to Projex, the IMechE, and the University of Huddersfield for facilitating this series of lectures. So please do bear in mind that tonight's presentation is number 8 in what was intended to be delivered as a journey around the steam and condensate loop. So I am going to go over some of the basic principles and concepts that we've covered off in some detail in those previous presentations, albeit at a quite a high level, just to act as a refresher or a reminder. So of course, we've introduced Spirax Sarco, who we are, what we do in some detail. Please do remember those calculators and configurators. They will be of some considerable use to you, not just for the basis of design, but also to help us understand and calculate our client's cost of steam. And that's a critically important piece of information to ask. What is your cost of steam? Because if we've calculated our cost of steam, we've got an understanding for the gas that they're burning to produce the steam and also what those carbon emissions are. So if we understand the cost of steam and we can then demonstrate the extent at which we've now reduced the demand for steam, we can understand what the payback is, both financially and in terms of those carbon emissions that we've now reduced. So as we've mentioned, it's the 8th in the series of presentations that we've gone through. So we're right at the very bottom of the page with regards to tonight's topic. We can call it STEAM, what the future holds, or we can really refer to it as an understanding of how we can generate decarbonized steam. And the title is specifically referencing the future, but we do need to bear in mind that the future, especially with regards to the steam systems that we're talking about, it is not too far away. It's imminent. So in tonight's presentation, I'm going to go through the basics of steam engineering once more to act as a refresher, and then I'm going to come on and move on to just a very small number of some of the technologies and some of the innovations that we can use to generate steam from alternative sources to natural gas or even oil. So I've introduced Spirax Sarco in the UK and Ireland. As far as Spirax Sarco globally are concerned, then I'm speaking to you on behalf of Spirax Sarco's Steam Thermal Solutions team that you can see sat in the column over towards the left-hand side of the box on the screen. But we've also got an electric theme thermal solutions stream. And that really reminds us that under the Spirax group, there's a range of different subsidiary companies that have got considerable experience in generating steam from alternative sources of energy. Typically, that's electricity. It can be renewable electricity, it can be grid electricity, it doesn't matter. So we've got those technologies within the Spirax group to essentially help our client decarbonize their steam requirement. We can help them move away from natural gas and generate steam from electricity. And when we can do that, that essentially means that the client's infrastructure, their boiler house, their water treatment, their steam distribution, and their processes can remain exactly as they were previously. Now, in very, very recent months, Spirax Sarco has also invested heavily in a company called Kyoto that manufacture molten salt thermal batteries, and also in SPH, Sustainable Process Heat, who manufacture high temperature, high pressure heat pumps that can produce steam. Now, there's no one magic bullet that is going to be suitable for every client's process. So please do bear that in mind. Every steam infrastructure is unique and different. And Spirax Sarco, we're not claiming that any of these technologies are going to be suitable and applicable for every steam using site and every process. But in many cases, they will provide a useful solution where our clients can retain steam, yet fully decarbonize. So I'm not going to go through the whys. I think that there's a glut of webinars out there that are really telling people why they need to decarbonize. I think we're already on that page. So what I'm going to look at today is the how. How are we going to do that? And I'm actually going to use ourselves, Spirax Sarco, as an example. We use a significant mass of steam at our own facility down in Cheltenham for testing purposes. We've got to test all of our products on high pressure, high temperature steam. So the consequence is we're burning a lot of gas and there are a lot of carbon emissions. Well, as a FTSE 100 organisation, we're part of the FTSE for Good index. So that means we've really got an obligation to our stakeholders and our investors to demonstrate how we're leading by example and doing the right thing and doing everything we can to reduce our own carbon emissions. And I'd be very, very surprised if the vast majority of other steam using organizations of any size, I'd be very surprised if they didn't have a very, very similar statement to the one that you can see on the screen at the moment. It could almost be copy and pasted across. So it means that we've really got to put our money where our mouth is. We've got to demonstrate that we're not just talking the talk when it comes to decarbonizing steam. We've got to demonstrate that we're actually walking the talk. So a lot of the technologies that I'm going to come on and discuss later on in the presentation, they have actually already been adopted by ourselves down at our facility in Cheltenham. We've actually moved away from natural gas. We've electrified our existing steam plant. So later in tonight's presentation, I'm going to tell you how we've managed to do that. And it means that we've then got a blueprint that we can take to our clients and say, this is how we've done it. This is how we've adopted these technologies. These are the lessons learned, and this is how you can follow our steps. So we've already mentioned that steam's used in a very, very wide and diverse range of applications. And we've also mentioned that in the vast majority of industrial applications, it's very, very difficult to find an alternative to steam because, as we know from previous presentations, steam can reach pressures and temperatures that it's very, very difficult for other sources of energy to reach. We know that steam is very, very densely packed with energy. We know that it's easy to control steam by means of manipulating the pressure, and it's easy to distribute steam as a small volume, high pressure media in a very small infrastructure and without any need to pump it. So steam's a very, very attractive source of energy. And there's an organization or a professional body known as the Renewable Thermal Collaborative. And the organizations that you can see on the screen are just a small number of those members. And these are manufacturing sites that are committed to reducing their carbon footprint, moving away from natural gas and other fossil fuels. But steam is a critically important component in the vast majority of these manufacturing operations. So they've got a vested interest in investigating ways that not only can they retain steam, but they can ensure that that steam is produced from carbon-free sources, so away from natural gas and fossil fuels. And Spirax Sarco is just one of the members of the Renewable Thermal Collaborative that are investigating ways that that can be achieved. So we've gone through the basic principles of the steam tables previously. I did warn you that by the 8th presentation, you'd be tired of seeing this particular slide, but hopefully it reminds us that not only do we understand the energy that the water needs to contain before it boils, we appreciate that when steam's condensed and given up its heat energy, it hasn't cooled down. That condensate is going to exist as a byproduct of heat exchange. It's high temperature hot water, and the energy content of the condensate is exactly the same as the energy that the water needs to contain before it boils. And that's demonstrated in the orange box. And we've also mentioned that the energy that we need to add to the boiling water to make it evaporate, that's the useful heat energy. So a lot of the technologies that I'm going to come on and discuss in this evening's presentation have really got their fundamentals in the basis of the steam tables themselves. But please, please do bear in mind those very, very first principles that we discussed at the start of our journey in September. The steam tables and the values expressed in the steam tables, they're only applicable if we've got 100% dry saturated steam. If we've got steam that sits on that dry saturated steam line. If for any reason, if we've got wet steam, then not only are we going to get those mechanical issues, that erosion, corrosion, and water hammer, we're going to have those inefficiencies. Well, tonight's presentation is about decarbonizing steam. So I'm going to ignore the issues, the mechanical issues caused by a poor quality of steam. I'm going to focus on the inefficiencies instead. So we remember, if we're generating wet steam, that steam is far more likely to condense out in the infrastructure. We're going to get a reduced mass of steam available for the process. So that distribution loss, well, we need to keep it to an absolute minimum, because if we don't, the boiler's going to be working harder and harder to replace that steam that's being lost. Our cost of steam, our cost of gas, and those carbon emissions are going to increase significantly. And we also know that if we've got very, very wet steam, there's less energy present within the steam. So again, the heat exchanger, the process is going to be calling for more and more steam to satisfy that requirement for energy on the secondary side. And again, the boiler's got to work harder, burn more gas, and there's going to be more carbon emissions. So please do remember that the fundamentals, they still have their place when it comes to decarbonising. The drier the steam, The less gas, the fewer carbon emissions. So we need to remember the basic fundamentals. And we've also spoken about what happens when we depressurize steam, and whenever we have steam that is lost to atmosphere across those flash steam vents. We remember that those flash steam vents are there not only to allow any passing steam to depressurize and be vented away, but it's also there because the condensate that exists as a byproduct of heat exchange, whether that be in the distribution pipework or at the heat exchanger itself, it's going to exist at exactly the same pressure and exactly the same temperature as the steam. So if we depressurize the condensate, then the byproduct is going to be steam that is produced as a result of that condensate boiling off. And of course, the rate of expansion is going to be significant to such a point that we need to vent it away from the condensate infrastructure to protect from damage. But when that happens, we've got a significant inefficiency because the boiler is going to be racing to replace that steam that is being vented to atmosphere. So we know that many processors, it may be absolutely the right thing to do for those thermal energy processors to transition from steam to an alternative, such as low temperature hot water. For example, low temperature hot water that could be produced by a heat pump. And like I said, in many cases, that's going to be not only attractive and the right thing to do, but if we transition from a steam system to a water-based system without giving it due thought and consideration, we could experience a significant number of issues and problems. So from previous presentations, you'll remember we've discussed that a kilogram of steam, because it's so densely packed with energy, it can carry approximately 50 times more useful heat energy than a kilogram of water. And we also remember that the only way water can give up its heat energy is by cooling down. Not so with steam, because when steam gives up its heat energy and condenses, the byproduct, that liquid condensate, is going to exist at exactly the same temperature. So if we can recover that condensate, we've got a really good efficiency head start in producing steam again. Other things to bear in mind with a steam system, it's a gas. So it's compressible. So high pressure steam, not only has it got a significantly smaller volume than a single phase non-compressible fluid such as hot water, but it's got 50 times more energy in it. So we need a considerable smaller, not just a smaller boiler, but also a considerably smaller infrastructure with a steam system than with a water-based system. And of course, when steam gives up its heat energy and condenses, the volume of the condensate is smaller still. We don't pump steam, it's a gas, but we need to pump hot water. And then finally, we know that there's approximately 4 times readily available energy present within gas than there is in electricity. So that means steam that's produced from natural gas, that can be generated and carry its energy to the process very, very quickly and very, very efficiently. So if we put all of those facts together, when we're comparing a traditional steam system to hot water that's produced by an air source heat pump, we need to remember, first of all, because there's far more energy in steam than hot water, it means that we're going to have to provide a sufficient number of air source heat pumps and at a sufficient capacity. We're also going to have to pump that hot water. So we're going to have to provide a number of circulating pumps that are also going to require an electricity supply. The infrastructure, we've got to rip out thousands of meters of steam pipe and replace it with an equal distance of a much, much larger diameter water pipe. Might be asbestos clad, might be in a difficult to access area, might have to go to landfill. That's not going to be very carbon friendly. But we also know that because there's more energy in gas and therefore in steam that is produced traditionally, we also know that we're going to have to size those heat exchangers on that maximum instantaneous demand for thermal energy. So I'm going to use the example of a hospital here. If we were producing hot water from steam in a hospital, that hot water will be available very, very quickly. The only way we could guarantee that that same mass of hot water would be available if we were producing it via an air source heat pump would be to ensure that we'd sized those heat pumps on that maximum instantaneous peak demand at 9 o'clock in the morning. That may mean that we need a significant overhaul and upgrade of the electrical infrastructure, which may mean that those heat pumps are no longer viable. So, as I mentioned, in many cases, heat pumps are absolutely the right thing to consider. But if we're transitioning from a steam system to a water-based system, all of those issues need to be taken into consideration. Okay, so when we're talking about a traditional steam system, I introduced the concept last week that that steam system could be 25, 30, 40 years old. So when that steam system was engineered, the cost of gas was cheap, the cost of water was cheap. No one had heard of carbon emissions. No one cared about carbon emissions or global warming. So the infrastructure was typically designed with a number of inefficiencies that we simply accepted back then. But today, the cost of gas and our environmental awareness means that we know where those inefficiencies are. So if we want to move towards a decarbonised steam system, we want to look at where those inefficiencies are and act on those inefficiencies first of all. It may well be that our steam boiler is producing 10,000 kilograms of steam per hour today. We may actually only require 7,000 kilograms per hour of steam at our process. So the first thing that we want to do is act upon those inefficiencies and reduce the work that the boiler has to do. It's going to be a very, very quick win and something that we can act on and realize today. The next step, we want to move forward and manage the steam system to make sure those inefficiencies don't start to creep back in. If we made the mistake of trying to rip out our existing steam system and engineer a completely new steam system on electrified steam, if we tried to do that based on our current understanding of the existing steam system, we'd simply be replicating those inefficiencies and the cost of the infrastructure would be significant. So it's vitally important that we follow that first step to optimize the existing steam infrastructure. So even before we take that leap to look at how and where we can optimize the existing steam system, it's important to ensure that we've got a good number of well-designed meters on each steam boiler. By understanding the mass of steam that's produced, that will help us understand our cost of steam. And when we understand how much steam each individual process or heat exchanger is consuming, we can then get a better understanding for where the inefficiencies exist between the point of generation and the point of use. Without steam meters, we simply don't have that data or that information available. So with a traditional steam system, we know where those inefficiencies are likely to be. So straight away, if we want to optimize the existing steam system so it can operate more efficiently, so it doesn't have to produce as much steam, so we can reduce the gas that's consumed and the carbon emissions, well, we know where those key areas are to optimize and to really give thought to. And we went through these areas in some detail last week. We spoke about ensuring that the steam traps were sized, selected, and maintained correctly. The reason being, well, we want to get as much of that hot condensate back to the boiler house as we possibly can. Remembering from the steam tables, the hotter the water going into the boiler, the less gas we need to burn. So ensuring that we've got the correct, well-designed condensate return infrastructure. We want to keep the steam as dry as we possibly can. Remember, the drier the steam, the more energy there is present within the steam. So we need to engineer the infrastructure correctly to allow that condensate to drain away across the trap. Simple things like separators. Separators dry the steam. The drier the steam, the more energy. The more energy in the steam, well, the boiler doesn't have to work as hard. Insulation, reduce that heat loss. 30, 40 years ago, when the steam system was engineered, it likely wouldn't have insulation because we wouldn't enjoy the payback. But today, we're more educated. We appreciate not only what the payback will be in financial terms, but also the extent at which we can reduce those carbon emissions. Boiler controls. We want to ensure that we're putting the bare minimum of hot water to waste in order to maintain the water chemistry. But most importantly of all, we need to keep an eye on those vents. Those vents give us an indication that we may have a number of failed steam traps. We may have a number of failed condensate pumps, and we're simply losing steam and also condensate. So there's a significant financial inefficiency if those vents are left unaddressed for any reason. So we've spoken about the reasons why we need to vent that steam away. We need to vent it away to protect the infrastructure from damage. But if we know the mass of condensate that is depressurizing and expanding, if we know the pressure drop, then we know the mass of steam, we know the volume of steam, we know the energy content of that steam. We can engineer different solutions to help us, well, to allow that expansion to vent away, but to help us identify ways in which we can recover that energy and put it back into another process. So that could be what we call an in-step process. For example, if we've got high pressure, high temperature condensate depressurizing across a failed trap, the flash steam that is collected by the flash vessel, that can be diverted back to a preheater in the same process, for example. That's what we call an in-step process. Or there may be applications where we can take the flash steam that is produced by one process, collect it in a flash vessel, and divert it to a completely different area of site, a different process. In the boiler house itself, that hot water that we need to purge or blow down from the boiler on a daily basis, that hot water, that high temperature hot water that's leaving the boiler, as it depressurizes and flashes off from the flash vessel, well, that steam can be diverted back to another heat sink, such as the hot well. In other words, if we can identify a heat sink that we can direct that flash steam to, it's free energy. The boiler doesn't have to work as hard, cost of steam, cost of gas, and the carbon emissions are going to be significantly reduced. So in a small number of applications, generally in the food, beverage, pharmaceutical sector, it's going to be attractive to consider moving away from a hot well, a feed tank that's operating at atmospheric pressure, which therefore means the maximum temperature can only really operate at 85 degrees or thereabouts. But if we can pressurize that hot water that's in storage up to 0.2 bar gauge, it means we can elevate the temperature of the water beyond 105 degrees. So you can appreciate there's going to be a significant energy saving there. And another benefit is by pressurizing the water, we've purged off a lot of the oxygen and the non-condensable gases, which you'll remember from previous presentations require a significant amount of chemical treatment, which is another reason why we then need to blow down that high concentration of chemicals. That's simply not required if we can pressurize the water. But better still, it means we've now got an excellent heat sink that we can direct those flash steam emissions to. So it means that we're moving closer and closer towards a zero net loss steam system. So quick checklist for you up on the screen. This will be available on the PDF if you'd like a copy of it later. Consider it an optimization checklist. These are the quick wins that we can act on quickly today with a proven financial payback. As I said, it's the wrong thing to do to look at those innovations straight away. If our existing steam boiler is producing 10,000 kilograms of steam per hour, if we can optimize the system so that the boiler now only needs to produce 7,000 kilograms of steam per hour, that's a very, very quick win. That's a huge step forward in demonstrating that we've started to decarbonize our steam system. And it's things that we can do here and now today. The next step really is to ensure that those inefficiencies don't creep back in. So we need to ensure that we've got a very, very robust scheme of routine energy system audits, steam trap surveys, and so forth. Better still, move towards some form of automation or digitalization. I think, simply put, it's I've used the analogy before. If we've got manual audits, we might only produce an audit once a year. So comparing a manual audit to some form of instantaneous digitalization, it's like comparing a photograph to a video. That means that we can act on any inefficiencies, not just months after they've occurred, but when they're at the point of starting to become inefficient or starting to manifest themselves. We can interrogate the system to understand how and where we can modify the process to bring around further energy efficiency improvements. So we can digitalize at an asset level, or we can digitalize at a site level. So some of the assets that we can digitalize range from individual steam traps to boilers to hot wells to condensate recovery units. We can get a much, much better understanding with regards to where those inefficiencies start to exist, and more importantly, what the payback is going to be in the reduced cost of steam, cost of gas, or by reducing the carbon emissions, for example. It really depends on what our client's driver and priority is. So it's only once we've optimized and once we've managed that we then want to move forward and look at, okay, how can we now switch off the gas? What can we do to completely decarbonize our thermal energy demand? So let's look at the point of generation, the boilers themselves. We know that hydrogen is an attractive source of energy because if we combust hydrogen and oxygen together, the byproduct is water vapor. There ain't going to be any carbon emissions. So in many cases, we can look at our existing steam boiler, we can get rid of the natural gas burner, we can retrofit a hydrogen burner, cap off the flue, there aren't going to be any emissions, and we can generate steam. All we've done is change the primary energy source. The water treatment, the boiler, the distribution pipe work, the safety features, the process, it remains exactly the same. Now, we're not combustion engineers at Spirax Sarco, but we do know that the only way a hydrogen burner is really going to be viable is if our client has got a reliable source of green hydrogen on site. Yeah, if they're producing their own hydrogen locally. If they're reliant on grey hydrogen or blue hydrogen, they can't truly say that they've decarbonized their thermal energy. Electric steam generators, standalone electric boilers or electric steam generators, very, very efficient, very reliable. They can get up to an accurate temperature quickly and reliably, very, very attractive. And this is what our sister company Chromalox produces. I think one of the drawbacks with an electric boiler is it needs to be sized in accordance with that maximum instantaneous peak demand for energy at 9 o'clock on a Monday morning. So in many cases, it's going to need to be significantly oversized to accommodate that peak load compared to the base load, for the simple reason that electric steam boilers, they can't respond as quickly as gas boilers, and they don't contain the same thermal energy in storage as a traditional gas boiler. But what we can do is we can move away from a standalone electric steam generator, electric steam boiler. And just as we can remove the burner from the gas burner from an existing boiler and replace it with the hydrogen burner, we can remove the natural gas burner and we can replace it with a series of electrical elements. We put those elements into the smoke tubes where those combustion gases would traditionally have passed down. In other words, we're electrifying our client's existing infrastructure. We don't necessarily have to go to the expense of a brand new replacement steam boiler. So the water treatment plant, the boiler, the safety features, the pipework, they remain the same. I must stress that this really depends upon the client's boiler being in a good condition. And of course, if we've optimized the steam distribution system already to reduce the massive steam that the boiler needs to produce, this becomes all the more viable. The issue that we have, well, it's exactly the same with the steam boiler itself. It means that those elements, they need to be sized to ensure that the boiler is capable of producing that maximum instantaneous demand for steam at 9 o'clock on a Monday morning. So we could electrify our client's existing boiler, as we've mentioned. It's what we call an electrofit project. It really requires the boiler to be at the appropriate condition. So if the client's got a natural gas burner that's 4 or 5 years old that they want to decarbonize, then it's likely going to be in a good condition. But if the client wanted to electrify a boiler that was 20, 25 years old, it wouldn't really be commercially viable. They would potentially need to look at a brand new electric steam boiler as an alternative. So a little animation for you here, just to demonstrate that concept. We take the front door off the boiler. We get rid of the natural gas burner. We don't need it. We replace the natural gas burner with a control panel. We cap off the flue. So we're bringing electricity onto the control panel. It can be high voltage. It can be medium voltage electricity. It really depends upon the client's preference and the nature of the electrical infrastructure locally. We can bring the boiler up to temperature very, very quickly. We've got a very, very even dispersal of temperature throughout the boiler itself. We don't need a purge, and we can get the boiler up to the appropriate pressure and temperature without those carbon emissions that are desperately important that we move away from. So that's what we call an electrofit project. There's another solution that's also very attractive for our client. This is what we call a steam battery. So if you can imagine a vessel of hot water or a vessel of water, we've got electrical elements running through that vessel. These are generally low voltage elements. So we can use grid electricity, we can use renewable electricity to heat up that vessel of hot water. Remember, there's a pressure temperature relationship. So if we elevate and pressurize to approximately 30 bar gauge, that's around 225 degrees. That water sits there, a single phase, high temperature, high pressure, until we need the steam. And when we need the steam, we can achieve it just by depressurizing that vessel. So this ties in very, very closely to the principles that we've gone through previously in the steam tables. So we're all familiar with the concept of batteries, electric batteries. We've got one in our mobile phones. We use it every day. Electrical energy, we can store power in the form of electrical energy. We can charge it up and then decouple it from the charge point and walk around with that mobile phone and use that energy when we need. We can use renewable energy as well, the great. The problem is that concept's of absolutely no use to us whatsoever when we need thermal energy. Accumulators, very, very commonly received in breweries and the chemical sector, for example, when we need a huge release of thermal energy very, very quickly. We pressurize that hot water using any surplus steam. And then when we need that surplus steam very, very quickly, when we need the steam for the process very, very quickly, we can achieve it by depressurizing that hot water. Fantastic store of energy. The problem is we would generally be using steam that is produced from a gas boiler in order to charge that accumulator. So as great as it is, it's not helping us with our decarbonising journey. An electric steam boiler, great as we know, it produces steam very, very quickly. We can use electricity. What it can't do is store that thermal energy, which means if we want to rely on an electric boiler, the risk is it's going to be sized on that instantaneous peak demand. It's going to be oversized for the vast majority of its operational condition. And that may mean that we need to overhaul the electrical infrastructure that's available locally to such a point where it's not going to be financially viable. So the steam battery, that brings together all of the benefits of the other solutions. We can generate energy very, very slowly over a period of 8, 9, 10 hours using a low voltage element. We can use grid electricity. We can use renewable electricity. If we've got renewables on site, whilst the wind's blowing, whilst the sun's shining, we're using 100% of that available energy to charge that vessel. When it's not, we can use grid electricity. We can charge using grid electricity if we're on a green electricity tariff during the silent hours of night. We charge that vessel of hot water to 30 bar gauge, 225 degrees, and it sits there until such a time that we need that energy. And we can achieve that energy simply by depressurizing the vessel. So that's my cheery, smiley little red face stood next to one of our steam batteries that we've got in operation down south. Many of you will think, well, that's a steam boiler. Well, that's the intention. It's manufactured to the same code, to the same dimensions. It's got the same safety features as a boiler. The only two things missing are, well, it doesn't have a natural gas burner and it doesn't have a flue. It's got that series of electrical elements that generate steam slowly, generate hot water slowly until such a time that that vessel needs to be depressurized to produce steam. So it's technology that the vast majority of boiler operators would be very, very comfortable and familiar with. So again, just a little animation to bring it to life off the page. That pressurized vessel, electrical elements running through it, we slowly elevate the pressure and the temperature. We can use renewables. So by elevating the temperature and the pressure slowly, we won't necessarily need the same electrical infrastructure overhaul as we would do with an electric steam generator or with an electrofit boiler. We're storing that energy until such time it's required. When that energy is required, we're just controlling it by using the basic principles of the steam tables. We're dropping the pressure to whatever the temperature the process needs the steam to exist at. So, for example, we have a client down south that needs steam to exist at exactly 121 degrees to satisfy the requirements of a number of autoclaves. At 121 degrees, the pressure temperature relationship tells us that we need to produce steam at 1 bar gauge. So if we're reducing the pressure of the steam from 30 bar gauge to 1 bar gauge, we know the mass of water that's going to boil off and produce steam. So it all really comes down to the mass of steam that the client requires to help us understand the size or capacity of the steam battery that we need to engineer. Now, as I mentioned at the start of the presentation, there's no magic bullet. There's no single one steam generation solution that is going to be a good fit for all of our clients. But it may well be that If our client had, for example, if they wanted to choose a brand new electric boiler, that would need to be sized to accommodate those spikes in that maximum instantaneous peak demand. But if they accommodated a steam battery, then a steam battery would be able to provide that huge surge of instantaneous thermal demand very, very easily. And it may then be that a much, much smaller electric steam generator or an electrified existing boiler was able to satisfy the requirements for the base load. And that in turn could mean that we now no longer need to have a significant overhaul of the wider electrical infrastructure. So this just gives you an indication of some of the capacities of those steam batteries. It really comes down to the mass of steam that the client requires and the pressures and temperatures. They generally are bespoke engineered. There's no reason why steam batteries cannot be banked if there's multiple processors, but a steam battery traditionally works very, very well if it works in partnership with an alternative source of energy, whether that be a gas-fired steam boiler or even an electrified steam boiler. So we really need to understand that the wrong thing to do would be to engineer that steam infrastructure, that alternative to natural gas, without having gone through the previous steps. We need to do everything we can to reduce, manage, and understand the mass of steam that's required. How much steam is required? At what points in the day is it required? At what point is a steam battery able to fully recharge before a mass of steam is required once more? Once we know all of the variables and all of those parameters, we're then able to look at what the appropriate alternative or what the appropriate solution is likely to be for that client that's got the intention and the expectation to be able to decarbonize their thermal energy. So, as I've mentioned, we've taken those 3 steps ourselves. We've completely removed gas from our facility in Cheltenham. We've got a steam battery in place to take into account those maximum instantaneous surges and demands for steam. We've electrified one of our existing steam boilers, and we've completely replaced one of the older boilers and put a brand new steam generator in place. So the 3 technologies that I've spoken about in some detail have all been engineered and installed down at our facility in Cheltenham. We've actually turned off our natural gas. We've got fully electrified, decarbonised steam. It's a project that's taken us 2 years to engineer and install, and let me tell you, it hasn't been cheap for 2 reasons. One, we know that the cost of electricity is currently about 3.5 times the cost of gas. So obviously that's going to have an impact on the cost of the steam. But we've had to have a significant infrastructure upgrade as well. All in all, it's cost us about £6.7 million in order to run this project. Now, that's not something that every organisation is going to have an appetite for. But when you're looking at FTSE 100 organisations or multinational organisations that have made a really powerful statement to the stock exchange that they will be net zero by 2030, that they will have 0 carbon emissions, yet steam is still critical to their process, this really presents them with a solution that they can consider. So, of course, if electrified steam is more expensive than steam that is produced by natural gas, it really emphasizes the importance of that first step. Let's reduce the mass of steam that is actually required. And that way we can make these electrified steam solutions a little bit more palatable for our client. So I've just put a few basics that we need to consider down there on the summary page. As before, for those of you that are currently in education, please do take a quick snap of that QR code down in the bottom corner of the screen. We typically take on a number of year in industry placements every year, and we offer permanent placements to generally around 20-25 graduates on an annual basis. So if you're looking for, or if you're interested in further information, please do click on that QR code. Failing that, I'd just like to thank you for your time in going through this series of presentations that have been presented in partnership with Projex, Huddersfield University, and the IMechE Yorkshire over recent months and weeks. Hope you found them of interest. If you would like a PDF copy of tonight's presentation, or if you'd like an attendance certificate, please do drop me a note on LinkedIn. Unfortunately, I don't have access to any of the chat functions, so that's the best way to reach me to make such a request. On that note, Brian, I'd like to pass over to you just to see if there have been any questions raised in the chat function.
Okay. Thanks, Dan. As always, that was brilliant. Really enjoyed it. You know, the cost of steam and understanding payback and what that fantastic bunch of companies that are all collaborating together. But I think for me, my takeaway was a new way to think about steam. So the future certainly will be interesting. We've had a question from Ian who's wondering about the elephant in the room, which is if steam's 5 or 6 times more expensive to generate steam than natural gas. How's that going to work? I know you've covered one or two bits and bats. I don't know whether you want to take a moment to reflect on that question and give an answer.
No, well, absolutely. Natural gas, it's natural gas is what is it? It's a quarter of the price of electricity. Natural gas is more efficient because it can give up its energy and produce steam more readily. The unfortunate byproduct is that natural gas is very, very carbon heavy. So organizations are incentivized, penalized, call it what you like. They are moving away from natural gas, and it is the right thing to do. The unfortunate thing is we've got to find an alternative. And the only real viable alternative we have at the moment is electricity. I mean, sure, we can use green hydrogen if if we've got renewables on site and we're capable of electrolyzing water to produce our own hydrogen locally. That's great if we can do that. But we're using electricity to produce hydrogen, and then we're using hydrogen to produce steam. Why don't we just cut out the middleman and use electricity to produce steam? As we've mentioned, it doesn't mean that steam is going to be any cheaper. It's not. The best thing we can do is ensure that we're not producing steam unnecessarily. By which I mean 20, 30 years ago, when we engineered the original steam system for our client, gas was cheap, water was cheap. We lived with those inefficiencies. We were quite happy to burn gas because we didn't know what carbon emissions were. Today, the best we can do is ensure that we're only producing, we're only electrifying the bare minimum of steam and at the appropriate times. So it comes back to looking at the process. What do we need? When do we need it? Once we know how much steam we need and when we need it, we can then determine what the appropriate solution is. Doesn't mean that steam's going to be any cheaper. It's not. But by producing the absolute minimum, we can make that pill easier to swallow.
Okay, thanks for that, Dan. Ian's also pointed out that low margin industries have had mixed results with going down this route. I guess it just goes to show that one needs to keep one's business head on when making decisions, and we're on a journey. And I'm sure as time moves on, the technology will move on, and more things will be possible. I don't think anybody thinks.
There are certain industries and certain sectors, Brian, that are they're suggesting that they can access government funding to move away from a natural gas boiler to an alternative. And quite rightly, they're rubbing their hands, thinking, "Great, well, if we're going to get this government funding, then why would we say no to move away from gas to a brand new, shiny, modern, efficient electric steam boiler? If we get government funding, that's great from a capital expenditure point of view. But of course, the operational running costs of that new capital equipment is going to be significantly greater because gas is 4 times cheaper than electricity. So it's an imbalance that we have in this country, unfortunately, which means that we are lagging behind other countries, but we're ultimately the ones that are under pressure to decarbonize as well.
Absolutely. Ian's also pointed out about hybrid systems should be an option, and as you agreed, Dan, that new thinking and keeping an open mind and making the right business decision at the right time is what we need to do.
Yeah, I
Not
mean,
sure.
hybrid options are, it's like this is one of the reasons why we as an organization have heavily invested in steam heat pumps and molten salt storage technology, for the simple reason that a manufacturing factory of scale in the future, they're likely to have two or three different methods of producing steam, because we've got to think a little bit more intelligently. And it may well be that, try as we might, we're completely incapable of moving away from natural gas for reasons I've mentioned. Perhaps it's that the best that we can hope to achieve is by reducing the natural gas that's burnt to an absolute minimum, but we still need it in some way, shape, or form.
Okay, thanks, Dan. We're moving almost up to 7 o'clock now, and you guys are between me and a kebab. Actually, I think that's what's for dinner this evening. Homemade, fresh produce, of course. If there's something in the chat, let's just see if no, I think we're done. So apologies if I've managed it on new post to see. Ben has asked, will steam batteries be suitable for hospital jobs where there is a continuous load, or will they need to be supplemented by gas/electric boilers?
Yes, they can be suitable for a constant load, but if they are, we will need to move towards a high voltage electrical element, and we'll need to ensure that there's enough thermal supply being brought on to ensure that the battery can be charged and discharged simultaneously. In other words, we're moving it towards a position where it is working as a electric boiler, but with an element of storage there as well. So it can, yes. It's just the controls and the charging that needs to be modified.
Brilliant. So there's a couple of messages come in. I think they're asking about getting copies of the slides, and I think what you said, Dan, was if they message you on LinkedIn.
Yeah, if you message me on LinkedIn, I can get a copy of the slide deck, and I can get an attendance certificate as well for those of you that would like them. That's no problem whatsoever. Like I said, unfortunately, I don't have access to the chat function, so the best way to reach me is just scan the QR that you can see on the screen, and I'll make that happen for you.
Okay, thanks, Dan. And if you're struggling to get copies, you can reach me at Projex Solutions, and I can work with Dan, and we'll get them out to you. We are recording all of these lectures. We'll be pushing them out via YouTube. So again, if you message me at Projex Solutions, we'll be able to sort that out. So it's just summarising a big thanks, Dan. 8 lectures. All of them fantastic. It was absolutely brilliant, interesting as usual. Big thanks to the Western Area IMechE committee and Nikki, who does all the back office organisation. Thank you to Huddersfield University, who hosted the first one face to face, and that was super. And I think the indications are we'll do the same again in the next academic year. I'm not going to remind everybody that there's a next lecture because this was the last one. So have a nice evening, everybody, and hopefully you enjoyed the lecture. Good night.
Great. Thank you. Thanks all.